Okay, let me record first. Okay, the record is now on. And from the previous example, I shouldn't have scrolled down. Let me go back here. You see that we are repeating ourselves in at least in the region that we can call the simple end support. Yeah, okay. We all know that in the end, the moment here must be zero. So why say distributing moment back and forth, back and forth, back and forth, back and forth? There must be a way, and senior citizen already know this. Junior doesn't know it yet, and not many of them show up today, so they're gonna miss the part where make their lives easier. Poor thing. Okay, so let's go and visit our handout, because you know we have a way to solve the simple end support. In the slope deflection, we have the new equation, the modified equation, right? And likewise, we can, in moment distribution, we can take a look, and it is kind of a more sensible, if you ask me, because let's say this is your simple end, okay? Joint I, and now I can look at the slope deflection equation. Mij is like this, and we don't care about the side term anymore. Okay, so just squeeze it out, and Mji. Now remember that joint I, we are looking at the joint I is a simple end. Okay, I hope you are familiar with this now. It's the end support that is also a simple support. That's why we call it simple end. Okay, so when we write this slope deflection equation, you have Mij, so this one is for your simple end support, right? And then Mji just for another support, the adjacent one. And when you solve this, what you have, remember that I used to mention that when you have the say nothing else, and you can see the relationship between the two rotations now. That zeta j is always equal to minus zeta I over 2 when you solve this. Okay, so we can rewrite zeta ji as by replacing this. Okay, because Mij is 0, right? When we solve this, we will get Mji is equal to 3ei over L multiplied by zeta I. Okay, let's say if I say 3ei over L is k, so this can be rewritten as k modified and then zeta I. But you should be able to recall by now from the way we prove the moment distribution that the typical stiffness for your structure under bending is 4ei over L. Okay, so when you compare this 3ei over L with 4ei over L, now you know that the member with simple end support like this has the stiffness 75% of the normal member, because Mji is 3ei over L zeta I, compared to the typical M, it's equal to 4ei over L multiplied by zeta. Okay, so it's 3/4, and there we have it, the modified of 0.75. So when you have your relative stiffness and you use this modification, it means that the problem with the simple end support is taken care of instantly. Okay, so without further ado, let us take a look at the first example related to that. This is the empty page. Okay, so here we are. It's another example to demonstrate how to take care of the simple end. So now you see we have two simple end support. So now students like you have a choice to make. You can carry on and solve this as a normal problem, which means you have to go back and forth between the simple end supports. Let's give it some name. A, B, C, and D, okay? If you don't do any modification, you have to go back and forth to supports A and D, and that makes your life miserable. But if you realize that support A here is simple support at the end, support D is also simple support at the end, and both supports we have moment equal to 0 in the end, so we can do some modification. So let's say before we do that, let me demonstrate something to you. You can compare this to this. Let's say if you have the same beam, use green. But if my support is like this, the same beam, but instead of having the simple end, I have a fixed end. The modification K equal to 0.75 tell you that this member AB with this support at the end as a simple support is 75% as strong as this member. So let's say the strength, the stiffness of this member is set as 100%. The stiffness of this member, because of the presence of a simple end here, is only 75% of a, say, a member with, say, full stiffness, because it has a fixed support here, and then this is a rigid joint. Okay, it makes sense in many ways. I'd say it makes perfect sense to realize that, okay, because of this, your member is now less stiff, because certainly it can rotate more due to the simple end support. It's going to rotate like that, but this is going to be zero rotation. It comes down like that. So this member is more stiff than that. Okay. So I'm just going to erase this, get out of the way. Okay. Or maybe I should keep it. Yeah. And I'll move it instead. On top of that. Okay, so you can see that we now have a weaker structure due to the presence of the simple end support. So I'll try to find some space and develop my relative stiffness, which is step number 1. Okay. So let's say my KAB is now I over 6. My KBC, because ER is constant, becomes I over 7.5, and my KCD is 1I over 4.5. You can modify now, you can modify after you have the relative number. So let's say I'm going to use K equal to I over 90. So I'll multiply everything by 90. So now I have here KAB is 15K. KBC is 12. K and KCD is 20K. But now you see the simple end support condition here for support for member AB and member CD. So certainly I can now modify this KAB and KCD by multiplying them with 0.75, right? So the modification would lead us to this being equal to 11.25K. Is it too small? And here becomes 15K. Okay, so now we are going to use this to calculate our distribution factor. So step number 2 is DFs. So distribution factor for member BA, you know, the summation of sigma, the summation of KB is 23.25, right? So DFBA is 11.25 over 23.25. Let's say we're supposed to, for a better number for this, because we have only decimals, right? So it would be a better idea to use 3 decimals. Maybe 0.484, and the DF of member BC, now it's going to be 12 over 23.25. That is going to give us 0.516. Okay. Next one is the distribution factor of member CB. The total here is 27, so it's 12 over 27. And for distribution factor of member CD now, it is 15 over 27. Okay, so that is a lot of 4 here. 0.44444. That means this is 0.556. Okay, is there any question around here? And the step number 3, fixed end moments. Okay, so FEMAB. You know, you are at least the junior. You guys are 3rd year student now, and yeah, even senior too. Some of you still cannot calculate the fixed end moment, which is a pity, you know. FEMAB. I'm running out of space trying to squeeze this in on the side. Okay, try to leave space to do the distribution. FEMAB is -5. Remember, we are near A, so the moment is greater, so it has to be 4.5 squared. 1.5 divided by 6 squared. This is minus 4.22 ton meter. FEMBA next. Now it's going to be plus because it's on the right. So it's 4.5 is already square. So that has to be 1.5 square instead, right? And then 4.5 divided by, say, 6 square. And that is 1.41 ton meter. Okay, and the last one is the FEMBC, that is minus 4.5, 7.5 square over, over 12. Okay, that is minus 11.09 ton meter, and this is equal to minus FEMCB. Okay, now I am moving down the side so much you guys cannot see the top anymore. So I'm just going to freeze it here a little bit so that you can have these numbers. Okay, and then let's wait for half a minute before we go back up and try to do the moment distribution on this one. Okay, now let's say we're going to start now. Okay, so yeah, let's how to draw the line. Okay. And now say, maybe use it, yeah, within the line. Okay. I only discovered this by accident, actually. You can do this stuff. Okay. So now we can put our distribution factor on here. That's going to be 0.484. You can write 0.48, you know, but when you do the work, you may use the 484 instead for better results. It's 516. That's 0.44. Okay. And that's 0.56. Then we have our moment to begin with. That is, this is minus 4.22. EA is 1.41. That is minus 21.09 and then 21.09, and here is 0. Okay. And let's say, okay, of course, we still have the distribution factor here equal to 0. Remember that we have modified our stiffness. So what do? Of course, the fixed moment is still there because, you know, we have the external load. But what we can do is we can balance this right away. Let me use different color. 4.22, right? That's what we need. We all know that. And that is 0. Okay, so that is probably the end of our first cycle. Or not yet. We have to balance the joint, some other joints as well. Here, the total moment is about 19 something, right? In fact, minus 19.68. And 48.4% is going to come from member BA. So here is 9.45, and that is 10.23. So again, don't forget that after you have balanced the first cycle, you can always check the equilibrium. The summation of this must be 0 because you sum this up. You get the negative value, and then you balance that by the opposite value, which is the positive, right? So here must be equal to here. If you do it right, it should be 0 after each cycle. And you can always check the left and then the right must be equal and opposite as well. So we move on to joint C. Now we have positive 21.09. That means we need the negative value, right? That's going to be minus 9.28. Here is minus 11.81. And that is 0, so I don't write it, okay? So now we are done the first cycle, okay? Remember that you can always check that, okay? And now we are going to carry it over, right? You have to carry over still, but because we modify this, so we don't carry 9.45 here. We don't. We do not do that. Some students who want to use modification and yet they perhaps do not practice, they get confused. And then they, after they modify, they still carry on as usual, which is not good, almost fatal, I have to say. Okay, so we carry this back. Here it's going to be 2.11. The purpose of the modification is just to realize that this member is weaker than usual, so it contributes less. Okay, so once you do that, it becomes something like a fix, but with 70% less I mean 25% less, with only 75% of the stiffness. So we don't go back there, okay? We carry the moment over here. We carry this over. So that's going to be 5.12. And then we carry this over. That's minus 4.64. Okay. And again, we do not carry this over. Okay, we don't. So now we have it. So it's got a new set of unbalanced moment. So we go again. Okay. The summation here is about minus 2.53. So you need positive 2.53 to balance this. And again, we use this factor. So you get about 1.21 and 1.32 here. Again, the second line here is equal and opposite to the first line, right? So the total moment here must be 0 still in the second cycle, and the left must be equal to the right, but opposite. Okay, you can always check yourself after each cycle. There's no need to hurry. And we move to joint C, you need minus 5.12. So using the distribution factor, you get this equal to minus 2.25. This is minus 2.87. Then you're done. You see, it reduces a lot of work because you don't have to go back to joint A and D. So it's now only the work between these two joints. Carry this over, carry that over. Okay. That is minus 1.12, and that is 0.66. Okay, and do it perhaps one more time. 0.54. 0.58. And here's minus 0.29. And here's minus 0.37. Okay, so that's it. And here the number is quite low compared to the beginning value. So I say, yeah, I'm going to stop for now, and then for the sake of demonstration. Here the summation is 0. Summation here is 14.7. That is minus 14.7. Here is the 15.1. That is minus 15.1. 0. Done. Just like that, right? See how good Professor Hardy Cross is? It just makes life so simple. Think about it. If you don't have a computer, this is the best solution to do, right? So now we move on. Maybe this is your step number 4. If you want to be, say, precise with your step. Step number 5 is free body diagram, maybe. So we have this. Moment. Say I can use different colors, give you different feelings. Okay, it's 14.7. All right, we have that. 5 tons. And many students will start doing things the way I do. It's just solving this by using superposition. It's kind of beautiful, you know, and it gives you a sense of, you know, what creates what as well. So midspan, you have this 14.7 in opposite direction. And here is positive 1, so clockwise 15.1. You have the uniform load. And here the last span, you don't have any external load, just moment. Okay. And from this now, you can say solve and get the shear. I only have the final number to speed things up. So that is 1.3 tons. This is not the reaction, okay? It's the shear, 3.7. Some of you are so good to complete the reactions, but in the end, we always use shear to design the structure, right? Not the reaction. Here is 6.8. And, 16.8, I'm sorry. Here is 16.9. Here is equal opposite, 3.3 and down. So I use the green one to know that, okay, that's the one that you have to calculate and achieve. And say, now you can do your quick work with the shear force diagram. It's going to look like that, right? You can draw them separately. You draw them all together. Doesn't really matter. In the end, after you draw them separately, you don't have to say combine them in the end again. You know, you don't need to. Okay, you can just draw them separately like this and save your time. Move on to do other things. Okay, there's no need to draw them separately and then combine them again in the end. All right. It would mean the same in terms of, you know, analysis, because we all have the results that we want. I mean. Okay, so the bending moment diagram should look like that. Here's you know, look at the direction of the moment. It means that you have the negative moment like that, and whether or not this turns out to be positive, you have to calculate. I think you guys are quite capable, because the last time I graded the homework, most of you, if you perform the analysis correctly, most of you got the diagrams correctly as well, except some would miss the maximum positive moment at mid-span. That's all. Okay. Now you can see the bending moment diagram. Here you have a negative moment, right? Look at the sign here. You know it's negative moment. Here is also a negative moment. It underlines the fact that when you have the the support, when you have the support like that, the only way that your structure can bend is this. Okay, it's only natural to have the negative moment and the support under, say, the downward load. Okay, and whether or not you have positive moment depends on, say, how big the negative moment is, and how which also relates to how big the load is in all those spans, and how long your beam is. Okay, in this case, it's pretty clear to see that yeah, you have your negative moment here, which is correct, which means your beam deflects like that. And here at mid-span, the load is pretty heavy, and the span itself is pretty long, so it has a chance to go back here and inflex and have the positive moment in the end. And now you have a simple end, it has to go down like that. So you better have point of inflection somewhere, because at the internal span, at the internal supports here, it has to bend negatively. Okay, and here likewise, it has to come with a positive, and then somewhere point of inflection. So the numbers reflect the behavior of the structure, and if you combine this with slope deflection, you would see that, okay, the rotation would make sense as well. Okay, so is there any question? So that's it. The use of simple end support to help speed things up, to help you say do less work. And when you do less work, it means that you are less susceptible to making mistakes as well. Okay, you can try to go back to this problem and try to handle support D here by using the simple end support to see if you're going to get the same result, which you should. And it's going to take a very, very short time to do it as well. You can, the best thing to convince yourself just to do the good old approach without modification, and then the new approach with modification, and compare them, just to give you a sense of confidence that you can actually use modification, and you would love it because it saves a lot of time. Okay. So, is there any question on this? Any question? See, this is not a very good ending, because see, if you see this number, it's pretty big compared to that one. So you may want to carry on for 1 or 2 more cycles. Okay. Now let me tell you here that if you see it like this is a very bad example by me. And this number, it's still too big compared to that. Say, and you stop. I would take points off, and you shall not proceed from this level, simply because you don't recognize the fact that you need to go on. Okay. So it's better that you go on, maybe 1 cycle, because the number coming in from here, it's going to be only minus 0.15, and then the next cycle they bring this number down dramatically. Right? Doing generally, I give 40% here at the calculation of moment distribution, if I'm not mistaken. But if for those of you who do a very harsh job, you know, you're not gonna get up to that mark, and you're gonna be stopped here as well. So what you do afterward is useless. Make sure that you recognize the importance of significant figures and the importance of the error. Okay. So is there any question? Hello? Okay. It's all quiet. So we have more modification. Of course, we cannot fail to talk about symmetry, right? And symmetry is here, okay? Whenever we have asymmetric conditions, we must always try to take advantage of that. And similarly, now there are 4 kinds of symmetry, okay? So that would be symmetry at the center of the member, meaning this is when you have the odd number of spans, right? Like 3, 5, 7, 9, 11. For example, if you have the odd number span, your line of symmetry is here, right? Oh, okay. So that will constitute in symmetry at the center of the member. So we're now taking a look at this particular member under the spotlight. And now you get this. Okay. Now you know symmetry would mean that your deflected shape would look something like perhaps like this. It has to be symmetric. Okay. So now when you look at the A, this becomes your A, right? That becomes your B. MAB is, this is again the slope deflection equation. You can remove this. But in this symmetric condition, we know that zeta B is equal to minus zeta A, right? So we can plug this in. So now you have this term I'm just going to erase this, get in the head a little bit. Okay. You plug in zeta B equal to minus zeta A. Now you have MAB equal to 2EI over L, zeta A. And if this is your K, now compared to 4EI over L, this K is half of the original K. So that means the modification factor is 0.5. Okay. Now we move on. This is you find this less, but they do have that in the past. Anti-asymmetric condition at the center of the member. So it's this picture again. See if I can copy it. It seems to work well of late. Yeah. Ooh, okay, got that with me. So got to erase that. Okay. Move this down. But anti-symmetry would mean that, you know, it's not going to deflect like that. So let me remove that. Okay. Instead, the anti-symmetry would mean that your structure must be symmetric, but your load is not. For example, like this. The load has to be equal and opposite. So this would give our deflected shape like this. This one goes down. This one goes up. And if it's going to be anti-symmetry, it means that your line of symmetry is in the middle again, right? So that means, incidentally, this will have to be equal and opposite, then they meet in the middle. And from this, we now can say the zeta A is equal to zeta B here under the spotlight here. Zeta A is equal to zeta B. They now rotate in the same direction. And you can imagine that. Look at, you are going to try to create the double curvature at bit span. So it is very difficult. And when you say, again, go back to this equation, but now zeta B is equal to zeta A. So you have 6 EI over L instead. See? Compared to 4 EI over L. So now K modified becomes 1.5. Okay? The next one is symmetry at the middle joint. That means now your number of spans become even, like this. 4, 6, 10, 12, and so on and so. So your line of symmetry is here. Okay? Now let me be smarter and try to copy this for the next case. All right, I'm going to use this for the next case. Okay, symmetry means that your rotation here, I mean, your displacement or deformation is going to be similar too, right? And whatever they may be, but they must be symmetric. So that means when you look at this, area of our focus, see, zeta B, because we call this AB, right? So that is A and that is B. Zeta B is 0, as you have experienced from slow deflection. Right? So to plug this into our slow deflection equation, excuse me, that one, zeta B equal to 0. So it means you have the basic term 4EI over L, which is equal to the original K. So here, K modified is equal to K. So modify or not, you already have very simple case to solve if you have the even number of spans with the symmetry. Okay, now the last one is of course anti-symmetry, where let's imagine you have something perhaps like this. Okay, so your beam is going to be like this perhaps. Ooh, this is pretty difficult to draw. Let's say, okay, like that. Okay, again, the area of focus is here. That becomes your A and that becomes your B. Now it's pretty much like having a simple n again, right? So theta B is equal to theta A over 2, and it becomes 3EI over L. So the modification is 3/4 again. Okay, you don't have to remember all this because I can give you, I can give this to you in the exam. But you should learn how to use it, especially this symmetry with the at the middle joint, or with the even number of span, or symmetry at the center of the member, or symmetry with the odd number of spans, like this. Okay. So is there any question? Maybe let's stop here. Okay. Question, please. Okay, I'm gonna pause the record.